Hello, everyone. Welcome to this technical session brought to you by Hamoye. I'll just like to briefly tell you about Hamoye. So Hamoye is an EdTech startup with a mission to prepare young professionals and college students for their choice careers in data and the future of work. We do that via our internship programs, which simulate the conditions we will face while working in the real world. Our internships will expose you to specially designed courses, career coaching webinars with industry experts, and industry relevant project presentations. My name is Ene Rudolph, and I'm a data engineer at Hamoye AI Labs. I'm joining you from Akwa Ibom, Nigeria, and I'll be your host for today's session. I'd like to welcome to this event everyone present, our incredible interns in the current cohort. Kudos to you for making it this far. Thanks to the Hamoye Fellows and the Hamoye team who have made this session possible. For this session, we have an industry expert, Mr. Oladimeji Mudele. Oladimeji Mudele is a postdoctoral fellow at Harvard T.H Chan School of Public Health. He obtained a Bachelor's of Engineering degree in Electrical and Electronics Engineering from the Federal University of Technology, Akure, and Nigeria, and also holds an MSc in Electronic Engineering. Oladimeji has a PhD in Electronic Computer Science and Electrical Engineering from the University of Pavia, Italy. His work centers on the application of geospatial information and data science methods for connecting climate and health outcomes as well as policy. He was the beneficiary of the Maria Sklodowska-Curie Actions and the German Academic Exchange Service scholarships. Between 2018 and 2019, he was a visiting scholar at the Argentinian Commission for Space Activities and the Institute of Computing of the Federal University of Alagoas, Brazil. In 2019, he received the Premio de Laurea Award as the top international scholar in UNIPV. As an employee at Voiced, he co-built a text-to-speech technology engine using deep learning-based methods, including convolutional neural networks, transformers, recurrent neural networks, self-supervised learning, adversarial learning, among others. So he'll be sharing his thoughts and experience on the topic correcting readings from low-cost air quality sensors using statistical methods. But just before I hand over to Mr. Oladimeji, please, I'd like for the interns to carefully take note of the following. Please feel free to post your questions and your comments on slido.com using the event code 1764720. The event code is 1764720. I'll say that again. The event code is 1764720. You'll find it in the comment section. If you prefer to post your questions and your comments in the comment section of Zoom and YouTube, that's also welcome. But please feel free to contribute to the session as you would. As you know, Mr. Oladimeji will be taking us through two sessions. First, the technical session, and then Q&A session where he'll be answering the questions that you have posted. A Google form has just been opened to collate attendance for the two cohorts. That's the fall 22 and the winter 23 present in this technical session. And the secret code for that form is pandas. So we have pandas, all lowercase. Pandas, that's the secret code you're expected to use. The form link will be posted now in the comment section of YouTube and Zoom. Is going to be pinned. And please, you're expected to fill that form quickly so that you can focus on the presentation at hand. The form, as you know, will be open for only 10 minutes starting now. So please, we encourage that you quickly fill the form and then focus on the rest of the presentation. At this point, we would like to hand over to Mr. Oladimeji to take over from here. Hello, Mr. Oladimeji.
Hello, and good morning, afternoon, and evening, whichever place in the world you're in. Hi, I'm in Boston on the East Coast of the US, so it's good morning from here. So yeah, I'm excited to be here today. I think so the time might be a bit short, but I think we should be able to have a good time. I understand some of you are actually probably late in the night now, so I would also try to ensure that I am not too dense in what I will be sharing, so that at least we could stay at as much as possible on the philosophical side of things, rather than focusing very deeply on, why, and the math and all this kind of stuff. Just try to talk about this problem and then use this problem as a motivating process. So think about how you can apply data science methodologies to solving real life problems around you. So I chose today's theme because I thought about a problem that I think I chose today's problem because I thought about a problem that I think affects many parts of the world, that people who are going to be in this cohort or on this particular chat would be able to actually interact with, and it's the problem of air pollution. So I'll share my slides now, and then we will talk through that that particular problem here. And please feel free to just drop your questions as has been said, and I'll take out. I don't know if it is possible to take questions twice. Maybe we do, because I'm going to be doing a slide presentation that I will run through in probably a few minutes. And then after that, I'd then go into like just showing you some code that kind of like tries to implement some of the things I'll talk about. It might be possible to like take the questions in those two boxes. So maybe first of all, considering questions people might have about, the theoretical motivation to the problem, description of the problem, because that's very important. I think it's important for people to actually have clear understanding of what we are trying to do, because then just jumping into code wouldn't make any sense if we don't have a clear understanding of what the problem is about. So if it is possible, I'd like to take the questions twice. So after I'm done with this slide presentation, I'd like to stop myself for a few minutes and then try to see what questions people have and address them. Then we get into the code, right? So I want to share my screen and then we get into slides that I have here prepared. So can you see my slide? Can you see my screen, by the way? You can just drop it in the chat if you can see my screen.
Yes, you can. We can see your chat. Your slides, sorry.
Yes, okay, cool. So I want to go into, so I should be in view and then full screen mode. All right, so let's go from the start of this presentation. So like I said, we want to have just a very light chat about time series modeling for air pollution monitoring, with a focus on correcting low-cost PM 2.5 sensor measurements. So don't over-focus on PM 2.5 right now, because it might sound technical, but we're going to break it down. And that's why we have the first session, which is, slide presentation, just to motivate the problem as clearly as possible. So yeah, I've already been introduced, so I'll just jump over this one, right? Yeah, so I thought I should add this, but I didn't know there's going to be an introduction before. So let's talk about the problem, right? Air pollution, it's simply defined as the contamination of the environment by chemicals that are harmful to human health, right? And some of those chemicals or physical or biological agents that are harmful to human health include the particulate matter, carbon monoxide, for example, from burning of fuel, right? You have carbon monoxide, and this is actually a very big subject these days when you're talking about climate change and carbon monoxide in the atmosphere, depletion of the ozone layer, all those things, right? Nitrogen dioxide, sulfur dioxide. Some of them come from industrial waste, for example, or if you live in places around Nigeria. I heard someone talk about being in Akwa Ibom, living in places around Nigeria, for example, where there is a lot of oil exploration, right? So there is the potential to have these kinds of air pollution agents in the atmosphere if the right policies are not put in place to control the actors in this field. So I will be focusing on particulate matter contamination, and that's what I call the PM 2.5. So the PM 2.5 is a specific kind of particulate matter. And the PM 2.5 specifically is defined as particulate matter with aerodynamic diameter 2.5 microns or less, which means they are very small, they are microscopic. And the fact that they are microscopic make them even more dangerous because they cause many negative health outcomes for people who inhale them from the atmosphere. And these outcomes could include asthma, chronic obstructive pulmonary diseases, and the likes. And you could have things like coughing, sneezing, and all that. And the sources of this kind of pollutants in the atmosphere include things like burning of wood for coal power plants. I mean, especially if you live, for example, in places in Nigeria where there is a lot of oil exploration, in places in India, for example, where there is a lot of congestion in traffic, right? There's a lot of people living in the city and people drive, so that also creates, right, air pollution in the sense of, PM 2.5. So yeah, I want to use the US as a motivating domain to then address this problem, right? But then you could just follow some of those processes if you want to apply this kind of solution to the context of your own country. You could just think about the problem in this way, right? So why are you doing this? First of all, you're trying to correct the readings of low-cost sensors. So meaning that you have sensors actually sensing, the quality of the air. And why are you doing that? Because you want to meet certain standards, you want to, improve the environment for people, right? But how do you define improvement? At what threshold do you have to reach for you to say that, we have good quality of air, right? And these standards are normally set by the government, right? In the US, traditional air quality measurement is done using, standards established by the US EPA. And the US EPA actually sets 12 microgram per meter cube as the threshold for PM 2.5. So anything below that is a good quality in terms of air quality. And anything above that is something to worry about. And in fact, they've actually changed that, and they're discussing that actually right now. And there's a proposed change to reduce that to like 10 micrograms per meter cube, right? As a threshold for good air quality. And if you look at the US, for example, the reason for the reduction is that they found that in places where the underprivileged people live, right? For example, racially, the racial minorities, for example, live. You could have even 12 microgram per meter cube, or less, maybe 11 microgram per meter cube of particulate matter in the atmosphere, but still have very bad effects on the people, because there are also comorbidities in the people that could then exacerbate the effect of some of these pollutants in their in those people. So yeah, so in the US specifically, how you measure the quality of air specifically, or how you measure the quantity of PM 2.5 in the atmosphere, is there's something called the FEM or FRM based monitor, which is a very expensive monitor to install. And the point is, if it is very expensive to install, and you need a lot of these sensors around to be able to monitor the quality of the air, what then can you do? What you could do is, instead of hoping that you could get a lot of budget to then install all these FEM and FRM monitors, what you could do, and this could even apply to places like much less resourced countries like, Nigeria or India or, African countries. Because if these FEM monitors are very expensive, then what is the way out? You want to use low-cost sensors. And the problem with using low-cost sensors is that the readings you get from those low-cost sensors are not very accurate. So essentially, what you want to do is you want to calibrate them. So this is the problem, right? You want to then calibrate these low-cost sensors. So by calibrating them, what do you achieve? You achieve, good sensing quality at a much lower cost. And so what are the ways to correct the readings from the sensors? Specifically, you could correct them, in laboratories or, some laboratory calibration and all that, which are very expensive to put in place also and to scale. Or you could use statistical methods to correct them. And we're going to be focusing on the statistical methods for correcting the readings from the sensors. So what's the problem? The problem is you have you live in a place you're concerned about the quality of air there, right? You want to monitor the quality of air in the sense of, PM 2.5, but you can't afford to install FEM or FRM monitors, which are very expensive. So what do you do? How do you address this problem? You could have one or two of those kind of FEM and FRM sensors. For example, airports, embassies do have these kinds of sensors at times. So you could have one or two of those, but then you could supplement those one or two with a lot of, low-cost sensors, right? And then you would use the FEM reference monitors to then statistically correct the low-cost sensors that you have, placed in the same vicinity as the FEM sensors. And then you would then use that statistical model, that correction model that you have obtained from, low-cost sensors that are co-located with expensive sensors to then correct all the other sensors that are not necessarily co-located with any FEM. And that way you have scaled, your air sensing or your air quality sensing capabilities. Yeah. So essentially what you have is a model that takes in the readings of your low-cost sensors, that's YL, and then also takes in X. X is also some other properties that define that environment, because at times the correction might not depend only on the readings from the sensors, because these sensors do not just specifically only read the PM 2.5 in the atmosphere, they also measure other kinds of things. And these things can actually affect, what is measured. So you also want to take some environmental conditions around, and then you take all of that information, you put it in your statistical model, and then it gives you a corrected version of the PM 2.5 in the atmosphere. So I want to introduce a project called the Denver Love My Air program, which is something that is very interesting. Actually, it's done in a city called Denver in Colorado in the US, and the idea is to empower communities with local air quality data using a network of local sensors, right? And then putting these sensors in schools because they want to improve the quality of air in, public schools around, so that children in schools can, breathe better quality air and then, be healthy, learn better and all that. So the data we will be using for what I will be talking about today comes from the low-cost sensors that have been put in place for those particular projects. Yeah. So yeah, and a study has been done using these sensors, and what I will be presenting is just some of the results or some of the methods that have been applied in that specific study, right? And this is that study. Okay, so yeah, so let's get into the work we want to do for today. Now, the work we want to do for today is we want to now look at the Love My Air sensors, right, which are low-cost sensors, and then try to correct the readings from those sensors. And how we're going to do that is we're going to use a statistical method to be able to know if your readings have been corrected. Some of you who are well advanced in your data science journey understand that for you to be able to do that, you need some ground truth and say, okay, this sensor readings have been corrected. How do I know they have been corrected properly? How do I measure the certainty of this correction? Meaning that I need to have some ground truth. And what is my ground truth in this sense? My ground truth in this sense would be the FEM or FRM sensors, which are the expensive one I spoke to you about. And then it's important to state that these sensors provide readings every hour, right? So, and that's the nature of our data. And in terms of locations of the sensors, inside the city, right? Imagine you're in a place, you're in a city now, you want to put sensors around to monitor the air quality. Of course, you don't put all the sensors in one location, you spread them around town. You spread them around town so that you can have a very much dispersed collection, so that you can see from the whole spectrum of the city, what is the quality of the air in the city, right? The data we are going to be looking at covers August 2018 to May 2019, because that's the period when the data has been collected, and the data was collected hourly. So you have a year, right? A year of data collected hourly, meaning that for every day you have 24 or 23, more or less, right, readings from each of the sensors specifically. And how many sensors do we have? So we have 5 of them, essentially. We have 5 of these sensors. Now, you need to also think about some of the goals of the study. And one of the goals of the study would be that you want to correct the readings of your low-cost sensors using statistical methods. And then after doing that correction, what do you want to do next? You want to then use your statistical methods to go to new locations and new sensors that are not specifically, co-located with your ground truth, right? And then correct those ones. So in that way, your study design has to incorporate the fact that how you define your training and your test data, because now you're not trying to predict in time, essentially. You're trying to expand in space. So meaning that your data splitting for training and test has to be spatial. So if you have 5 sensors, 5 low-cost and sensor locations, what you want to do is then, instead of splitting in time, you could say, okay, you know what, we are August 2018 to May 2019. I would train from August to January. That is in the case where you are interested in time extrapolation, but that's not what you're interested in here. What you're interested in here is that you want to be able to extrapolate into new locations, so that whenever you buy a new sensor now, right, in a new location, you could just apply this statistical method to it and it will correct it. So you split your locations rather than split on that time. So we have 5 locations, 5 low-cost sensors, and we want to split them and say the training one would be 3, and then the tests, right, where we actually measure and evaluate and say, you know what, I think my correction method actually does well, or does well enough, right? So in those 2 locations that the model will not see. Right. So I mentioned earlier that when you want to do this kind of statistical correction, you want to, so your model, whatever it is, it could be a linear model, right? And that's actually the simplest way to go about this. You have a linear model. So your model has to see a couple of things. First of all, it takes in the reading from your low-cost sensor, right? And then it takes in certain characteristics of the environment that can influence those readings, because you want to control for those in your model. And then the output of that model is a version of the sensor reading that is corrected specifically. But what are the things that we want to put in our model? That's the question. How do you come up with things to put in your model for anything you're trying to do, for example? So in this case, it's just, I should specify actually, when you see air now is the low-cost sensor, and then CS is the actual reference sensor, which would be our ground truth data set in this case, right? Right. So no, that's the other way around actually. Yeah, so CS will be a low-cost sensor, and air now will be a reference sensor. So how do you decide what you want to put in your model? In any case, in a generic data science task, you have to predict something, right? But you need to account for certain other features of your process in your model to be able to get a good prediction. What you do generally is you go to the theory of sensing of air pollution, and you ask yourself, what are the things in the environment that affect air pollution specifically? What are the things in my environment that affect the pollution in the air? And then you account for those things in a model so that your model can be more robust. And some of those things that we found is temperature, right? Humidity, right? Distance to the highway. So what does that mean? So if a sensor is placed beside the road and another sensor is placed somewhere in the forest, you expect that theoretically the one that is placed at the roadside, especially a very congested road, also depending on the kind of road, so you can account for also the kind of road, because highways are more more heavy duty kind of traffic. So those ones might, might put more pressure on the environment in terms of air pollution content generation. So you want to account for that in your model. So you say distance to highway, for example, and it from our own, from the 5 locations where we have the sensors, there is 2 of them that are nearer to the highway. And in fact, some of the things you could do actually before you do modeling is you could look at your data and say, so just the locations of this place, you could plot them, just partially and look at how close they are to the highway. And you could actually just look at the amount of pollution that is measured in those locations. You could, just sum in over time for all the locations and check. And you could see that maybe your hypothesis that a location that is closer to the highway is actually should actually does provide more pollution, right? And then what are the other things that actually affect your model? It turns out that the cyclical values of time, hour of the day, they help you to account for things like seasonal and daily variations. For example, in Lagos, Nigeria, or Delhi in India, or cities that have heavy traffic, right? What happens is that when people are going to work in the morning, the road is heavily congested, right? And during noon time, when maybe most people are stuck in their offices, there is less traffic on the road. So you would expect variations also as a result of this. So you might want to account for that. And there are a couple of ways to account for that. I'll talk about them when we get to those places. Yeah. So I've already mentioned the goal before, and we want to generalize into all seasons of the year. We want to generalize into new locations for calibrating PM 2.5 readings from low-cost sensors. So before we go into the just PET programming session, I'd just run through a few questions, and the first one would be: can we correct particulate matter 2.5 readings from low-cost sensors using data from synchronous collocated reference FEM sensors using a statistical model? The answer is yes. Yeah, but what kind of model would we use to do that? Could we use it? Do we need maybe a linear model is sufficient? Do we need to do something more complex than non-linear, maybe a generalized linear model, or we need to go into probably machine learning methods, or yeah. But what I do advise most of the time is when you're thinking through this kinds of problem, any problem you have, in fact, you want to start with the simplest abstraction of that problem and try to solve it in that way, right? And in fact, you don't want to start by modeling. You want to start by looking at your data and saying, let me see what is in this data. What are the things I assume should be there? You write those things down, then you check for those things and see, right? So the other time we were talking about location to the road, or for example, we were talking about day of the week or time of the day. You could do things like, let me average this data by time of the day, right? So the average readings from 10 o'clock in the morning, average reading from 11 o'clock in the morning, average reading from 12 noon, and then you just have this, and then you could do a bar plot of that and just look at it and see if it is invariant. For example, if you find that it's actually invariant and is all flat, then you don't need to account for it in your model because there is no variability to check for. But you want to see that, okay, actually, this thing actually grows. At 7 o'clock in the morning, it goes up, it peaks, and then it comes down. So now you see that there is some signal in that axis of your data. So these are the kinds of things you do. And then, yeah. And how do we evaluate this model? Model evaluation. So if I have a corrected prediction now from my model, what is the way to measure how the certainty of that prediction, right? So so these are the kinds of things we're going to get into, but we're going to be like focusing not on the code. Don't spend your time trying to look at this code that I have written. Why does it work? Just think about the concept and the idea and why we're doing what we have done. What's the guiding principles behind that? So I'll take your questions right now for the first section of our talk. If we have any questions, please. Are we there? Do we have the moderator there? Hello?
Hi, so yes, we are here.
Okay. Awesome.
Okay.
Okay, I'm trying to see. So how do I get to see the questions?
Okay.
We're going to have the questions read out to you.
Okay. Do we have any questions on the first session of this talk today?
Daniel is going to be co-hosting that session.
Okay.
Hi,
yeah.
Daniel.
I'm trying to.
Just run through this very quickly, because then so that we can jump into the other part of what we have to do.
Okay, then. Okay, as soon as this is done, we'll create the questions we have so far.
Awesome.
Then you can, yes.
Awesome. So I'm going to get into some of the code that that I have here. If you know, if you got information from which I believe you got from the organizers of the session, you know that I had sent ahead of time a repository that supports some of the theoretical stuff that I had introduced. All right. So I just wanted to show us how, the flow of work that I had to go into, how this problem was then approached, right? And that could help you to think about how you approach any data science problem specifically. So the first lesson 1 in the notebooks, I think we should already all have access to this, but if you don't, please specify in the chat so I could provide you with a link to it. Yeah. Okay, he said, can I say again what sensor is used to calibrate the low-cost sensor? Yeah, so you're using an FEM, it's called Federal Equivalence Method, but just imagine it as a very accurate, right, very reliable, right, sensing apparatus that is also very expensive. You understand? Yeah, so the problem is that it's you could also just set up that very expensive one and say, okay, you know what, let's not calibrate anything, let's have this very reliable one, but it's expensive to have that. So then what you do is you have maybe 1 or 2 of that, and then you use those 1 or 2 to calibrate a few low-cost sensors, and then you use that calibration method, that calibration model to then calibrate many low-cost sensors for that same location specifically. Yeah. So yeah, so let me provide a link to the GitHub. I'll go to I just open GitHub right now, and then so this is GitHub. I think I went to this stuff sometime today, so it should be up here. Yeah. So I'm dropping the GitHub repository in the chats. So if you can see my screen, you see this particular repository. It's just so if you look here, you find the repository, but don't focus on the whole thing right now, because it's a lot and it's too much for the time that we are going to be spending together. What I want to show you is I want to motivate how then we approach this problem, right? We have low-cost sensing, we have FEM sensing, which is the reference one, and then we want to use the FEM sensors to calibrate the low-cost sensors, and then we want to measure, the quality of our calibration. Okay, so now I'll be checking the chat from time to time. So I just want to look at, so the first notebook that is available in this lesson is just looking at what I call data preparation. So the bedrock of data science is data, right? And in fact, I feel like one of the most beautiful things you could do as a data scientist is to, at some point in your career, work on a data science project from end to end, meaning that you're not picking out a data that is available on Kaggle and you're just running models on them, or you're not picking out data that is available somewhere that you cannot relate to in real life because it has no meaning to you. You're just running models, and so what do your models mean? You don't have any ownership of that. So this first notebook is just thinking through the whole idea of data preparation. How do I clean my data and make it useful, right? And the first step to doing that is understanding the problem that you are trying to solve using this your data process. So what is the problem you're trying to solve? And when you ask yourself that question and say, what is the problem I'm trying to solve? And then you ask yourself also, you clarify to yourself, why is this problem important? You understand? Are there other ways to solve this problem that does not require doing, this whole data process? If there is already something to do that is doable now, that does not need me to like go and get some local sensors or collect data, like I could just do that and solve the problem and move on, right? Okay. So the first is understanding the problem, and then you now ask yourself, if this problem is truly and indeed important, what data do I need? What are the questions I have, right? You could have a question of, I live in Akwa Ibom State in Nigeria. Am I sure the air quality in Akwa Ibom, in different locations in Akwa Ibom, especially, looking at the, socioeconomic variables, also looking at, where rich people live, where not so rich people live in Akwa Ibom, comparing all that, do you think that, the air quality in that location actually is safe for human beings, especially in the long term, right? So that's a good question, right? And yeah, so you start from there. You start from a question, and then you can then ask yourself. Diving into data is a very important step, because you want to ask yourself, so is there data for me to answer this question right now somewhere that is clean, that is ready to be used, that I can just deploy, and then I am good to go and I am solving my problem? If there is no such data, then you want to ask yourself, how do I collect this data? So that's the whole point of this low-cost sensor. So someone thought about that and said, for me to be able to collect this kind of, someone is raising his hand. Can you speak, Banji? I think Banji is raising his hand. Right. Anytime you want to speak, you could just, Banji specifically, you could just interrupt me. So for example, you ask yourself, what data do I need? And then you now think of, how do I need the data to be arranged and organized for me to then be able to use it for anything productive in this question? So how should our data be organized in this case? In this case specifically, we want to have data, right, that is defined across time. So for each of the sensors, we have 5 low-cost sensors, right? And what do we want to collect from those 5 low-cost sensors? We want to collect the PM 2.5 atmospheric content measured, right, from each of them across time, every hour. It could happen to be the case that your reference sensor or your low-cost sensor do not have the same temporal resolution, meaning that maybe one is collecting every hour, the other one is collecting every 3 hours. Then what do? You have to align them in a sense, meaning that you could do averaging, you could check the maximum. I mean, these are the different ways to do things, right? You could average, and then you have to bring them to the same temporal resolution so that you can then work with them differently. And that's what I call merging. You merge different sources of data into a single frame. And then now you ask yourself, what are the other variables that I need to account for in my model? What are the other variables that you need to account for in your model? And then you need to realize that all those other variables that you want to account for in your model too, they have to come at the same temporal resolution as all the other data sets that you're going to be needing, right? So eventually what happens is that most data science projects, default to the lowest spatial resolution across all your key variables. So if one of the key variables is only available on a daily basis, then you want to have, you would have access to the slides after this session. So you want to have, then you want to bring everything down to that level. So this is the point. That's data preparation, essentially. And what you then do is you don't put a bunch of code together to get you your data. And then, like the question I asked earlier too, what are the key features and data and variables you need to have in that data to represent, what your model would actually be taking in? In this case, we have length of roads, meaning roads of different radius actually have different contributions in terms of air pollution. And then, time variables, you want to have temperature, humidity. It happens to be the case that the CS sensors, which are the low-cost sensors in this case, also measure temperature and measure humidity. And in fact, that's a very key, important reason why they have been included in the modeling, because you are assuming that the error that has been projected into the, let's say, for example, the error due to electronics, right, in the sensor system that has been projected into the air quality reading also reflects in the temperature and the humidity. So you want to account for those readings in your model so that your model can then be able to correct So essentially, what I have done in this notebook is just to do all of those things I described to you specifically. And one very important thing I want to quickly mention before we leave this particular notebook is that you could see here that I took the time to like define each of the variables. So after loading the data set, so I have this like sort of like a CSV file that has all this data set. So after loading all these data sets, after I have asked myself the question of what problem I want to solve, what are the variables I need, and after loading all of that data set, what did I do next? I went straight to then define every single variable in my data set. What am I trying to do here? I'm trying to match them to the data that I have already defined earlier as what I would need, right? Because then I want to be sure that the data I need is what is contained in my data file, right? Because else, I mean, it means that either I need to go and collect data, or I need to find a different problem that I can have data for, because maybe I don't have the data for the questions I want to ask. So in this case, you do that, you define all those variables, and then you clearly define them and say, you know what, I think I have all the variables I need to then, proceed to address this problem. And then you just set up you just clean the data sets. What are the things you want to check for when you're cleaning data sets? It's, for example, missing data. That's an important subject. And for example, maybe some sensors do not provide readings in certain hours. Maybe they were down, let's say, in a place where there could be interruptions for whatever reason. And then some hours of the day, you didn't have any reading. What are the things you could do? You could average, for example, take the one before and take the one after, add them together, divide by 2, then you get the one in between, right? Interpolation. Or because it's a time series, in this sense, that is useful. Yeah, but there are other ways to deal with missing data. But in this particular case, you could just deal with it in that way and say, yeah. And then you could account for time of the day, because you want to account for time of the day in your model. There are a couple of ways to do it. You could create dummy variables for each of the time of the day. And every signal that comes at that particular time would be 1. And then the rest of them would be 0. That's one way to do it, right? Or another way to do it is you just want to represent the cyclical behavior of time. And one way to do that is you're combining two variables, which is cos and time together, and then the cosine and the sine. If you combine the cosine and the sine in 2 dimensions, what you get is something that is cyclical like this. So anytime you want to work with things like, months of the year, hours of the day, you understand, things like that come cyclically, because there's 12 o'clock today, there's also 12 o'clock tomorrow, and 12 o'clock today and 12 o'clock tomorrow, you want them to mean the same thing. So you could just do something like, cyclical encoding, which is using sine and cosine, specifically. Yeah, so those are the things that was done to then prepare. So if you run all of this notebook, for example, what it does for you is brings you to a particular end where you save cleaned test CSV and cleaned training CSV, which are the clean data sets that you want to get from this step, because in this step, you're doing data preparation. So then what do you want to do next? You want to go to lesson 2, which in this case would be, now that I have clean data set, I want to explore the data and see what is in it, in fact, right? And why do you need to explore? Because essentially you need variability in your data to be able to have, all right. So someone is saying, Kenneth is saying that, sine, sine and cosine encoding. So the idea is so if you have 1 to 20, so 0 to 24 or 0 to 23 every day, those are the hours of the day. If you sort of put that in your model, right? So if I say time of the day, one of the variables one of the features in my model, and I say time of the day 1, time of the day 2, what your model interprets that as is that when the time of the day is 2, and relative to the time of the day being 1, it means that there's a step of 1, meaning that it's an ordered ordinal, how would you call that? It's an ordered arrangement of time, essentially, rather than looking at it in the cyclical sense that what I have at 1 o'clock today should be what I have at 1 o'clock tomorrow, or at least a baseline of that, right? Should be what I have at 1 o'clock tomorrow. So what you want to then do is you, rather than think of time as linear, you think of it as cyclical. So let's go back to the notebook. Actually, if you look at this, this is a very good explanation. Let me show you what happens when you do this cyclical encoding. just a moment. So if you go back here, you look at time. If you check time, look at hour, and you have a sample. So different samples, right? Let's say you take 50, you take some of the samples in your data set, and then you plot the time of the day looking at it in a linear way. What you get is something that grows like this. And then when you get to 24 hours a day, then you jump back to 0. And 24 hours and 0 are supposed to mean the same thing, by the way, right? But then you're seeing them differently, first of all, right? And then you go back again up and all that. But then, and also 23 should be seen as 1 hour before 0, right? And then 1 should be seen as 1 hour after 0, meaning that you need to have a cyclical encoding of this specifically, because now in this linear representation, what you have is 23 is so far away from 0. Essentially, you have 23 up here, you have 0 down here, and they are so far away from themselves. But that's not the case in real life, right? So essentially, if there is any effect of time, you should already have a ramp coming from 1 hour before that and 1 hour after that. If there is traffic at midnight, it means that traffic probably already started at 11 o'clock in the night too, and we should already be able to encode those as close to themselves. But if you look at the cyclical encoding, for example, what you have on top here is let's say 12 midnight, and then 11 o'clock, in the night is before PM, is before that, it's right before that. And then when you encode this, what you just get is, you get the cyclical overlay. And this is a very useful way to encode things like, time. There's things that occur, periodically. If you can represent them as a periodic functions, which is sine and cosine in 2 dimensions, this is what you get. Yeah. So I think we have to be very fast. So I jump into so exploratory data analysis. I just want to run through that very quickly. What are you trying to do? You're trying to check for variability in your data on certain axes that you consider to be important. And then you come up with questions too. What are you trying to check? And why are they important? Things you could check include, for example, okay, you know what, luckily for us in this case, we have the latitude and longitude of the sensor locations. Can we just plot those on a map and see? First of all, what are we trying to look at here? We want to see if these locations are actually dispersed enough far away from each other such that there's no spatial autocorrelation, essentially. Because if you have all the whole sensors just within, 500 meters, or I don't know, few meters away from themselves, 10 meters and all that, then you're probably just reading the same thing across different sensors. And I mean, you could just correct one of them essentially because it will be the same, right? But in this case, what you want to check is you want to see that, I think they come in different locations, and you want to visualize those locations. It comes alive in a sense. You could see that, this place is not this, I mean, so yeah, so that's one of the things you want to do. You want to check the visualization of your data and then plot that in the map, and then try to see if it helps in any way. So for example, I should try to show this one. Yeah. So you could see Denver. This is Denver, right? It came out 3 times. Anyway, let's leave that. So this is Denver City, and then you look at the sensors. So one of them is here. You can see this one here. This one is this I-25 GLO. This is one of the locations, right? It's close to the highway, so you could see that, right? And then you want to watch out for that. And then you look at I-25. In fact, Interstate 25. I-25 means Interstate 25, which are interstate highways. So that's how those locations are I-25. So those 2 I-25s are close to the highway, and then you might want to check and say, let me average my outputs from all the sensors. And then see, or maybe get a median value that is more robust to outlier measurement, and then see if what comes from I-25 is actually higher than the rest. Then that means that there is a significant contribution from traffic, because the fact that there is a road there does not mean that the road makes a huge contribution. Maybe there's no car traveling around that road. Maybe it's it's not a very busy, section of the country. So yeah, you could just do all these kind of things. So then you check. Also one of the things I didn't mention is that we included in this model something called the length of roads within a particular radius from the sensors. So let's say a particular sensor is at a location, then you take a radius, this is 500 meters. Then you look at the lengths, in kilometers of road that fall within that radius, right? So you see that, okay, camp has a high, as the highest amount in this case. So but also you could then check and see if, there is some contribution that shows. So look at this plot, for example, that I'm going to be providing now. We want to observe from this plot, we want to see what is the amount of PM 2.5 measured at these different locations, right? The average. And then we want to then check to see if it affects road length affects it. First of all, I have plotted here just the length of road within the 500 meter radius from each of this, and you see that camp as it is proportionately higher amount than the rest of them. So you just go down and then you check, for example, the mean the mean for each of these locations now. We have camp in our test data set. So we go there and we look at it, and we see that camp has a high mean. You also have a high, the I-25s in our first table here, the I-25s have, sort of like a bit of a high number, right, compared to NJH. And if you look at NJH, what is there? It says that it's a hospital. And let's go back to our plots. You see that it's somewhere here that's, very far away from the center of the city, from the large roads, and it's close to a park, right? So that means that there is not so much air pollution activity. So you could see, just comparing this kind of information helps you to, to get an idea of your data in that sense. You could check distributions also, just to see, the air pollutions measured across the different locations, and then look at the distributions of those, comparing across the different locations. And you see that NGH, for example, has a much lower range than the rest of them. Of course, it's far removed from the city. There's lower amount of activities happening around there. And then you look at I-25 and camp. So I-25 Denver is right next to the Interstate 25 road, and camp is, if you go back to the plots, camp is just in the middle of, residential location. And you see that the difference is actually large in terms of, first of all, the distribution, and then even the outliers and all that. So that gives you an idea that probably, this road actually makes, a high amount of contribution for Denver specifically, right? You actually makes some contributions, and it's a good idea to include, roads and road indicators in your model, right? So now you want to compare. So if you're trying to correct two readings, the first question you want to ask yourself is, do I actually need to correct this thing? If they actually both measure the same thing, right? So if I do a scatter plot, right, of both of them, just looking at the correlation between them. So I want to see, okay, maybe they don't both measure the same thing, but what's the difference? Do they correlate largely, right? So what do I need to do? For example, you see that there is a linear correlation in a sense. So that already gives you an idea that, you know what, I think I could just use a linear model to correct it. So you're doing bias correction here. So you see that the line of correlation probably is tilted a little bit this way. So you want to probably just drag it down a little bit so you can have something that crosses, both corners of your square that defines your plots, right? So so that's so you're comparing again. This is for the test data set. And then if you want to have a linear, so look at the line here. So this line, if you trace this line up here, it probably goes up here. So what you're trying to do is you're trying to shift the line down a little bit, and that's just essentially changing what essentially that means in a computational sense. Is if this line is defined by mx plus c, then you want to change m, and you probably don't want to change c because c is probably would be 0 because you don't have a bias from the bottom here, right? If this line has started from 25 up, right, then you know that there's a bias just by subtracting 25 from you don't even need a model for that, in fact, right? So this is why exploratory data analysis is good. Let's say this line or this points are started from like 25 up, and then they are perfectly correlated, but they just have this bias. So by subtracting that from all the values you get from your low cost sensors, you have done correction in a sense, right? Yeah, but in this case, it starts from 0, so you probably don't have a bias in terms of the seed, and you want to change the slope or the gradient of your line. Yeah, so these are the kind of things you check when you're doing exploratory data analysis. Then you could do this for all the locations and see if this relationship is changes across the different sensors with their reference sensor measurements. Right, and it sort of seems very similar. You see that the correction. So one thing that this shows you is that the error is not very much dependent on the location as much as it's probably dependent on the sensor that has been used, especially because you also know that it is the same sensor that has been, in fact, the same sensor have to be used right across the whole project. Yeah, so you could see, yeah. So that there is many of those kinds of things you could do. Let's just jump out of it. You could look at distributions, and yeah, it's the same as the box plot that we did the other time. Yeah, and then also you want to check things like day of the week. So what effect does day of the week have? So I've done a plot here that in between those blues, those whites you see are like weekends, but it doesn't seem obvious. It's not easy to actually see anything there. So what you want to do again is this: you want to check. What is the median PM 2.5 on a weekday? What is the median PM 2.5 on a weekend? So you see that day of the week actually plays a role, right? Weekends are, significantly lower than weekdays. In fact, right? So it means that you want to account for that, and this is how you build out your process. So understanding what should I include, what should I leave out. Yeah. So I mean, let's not spend too much time on this. These are the ideas. So let's go to the next notebook where I will be rounding up things. Yeah, I'm coming. I need to go to a different notebook now and then. Yeah. So what do you then do when you have that? Then you do modeling. You could use a linear model. So what your linear model does, the end of the story is that what your linear model does is what we explained the other time. We understand that the linear model just needs to rotate our data a little bit, right? So yeah, so I sort of feel like most people are familiar with modeling. So you just get a linear model from scikit-learn, and you have your X, and then you try to predict your Y. And how do you know if your X and if what you predicted is good? You try to compare that with your ground truth. You could use a mean square error, because this is a regression task, right? It's not a classification task. You use mean square error, root mean square error, mean absolute error, correlation, for example. I mean, the problem with correlation in this sense is that correlation will be very biased because it's scale invariant. And we already saw from our scatter plot that they are actually correlating even without a model, right? So if you see correlation there, to tell you that correlation is good, but that's not what you're trying to see specifically. Yeah. So if you check, for example, these models, then what you want to do again is you could disaggregate the models by sensors and check for each of the sensors and say, you know what, am I getting more errors in certain other sensors? And then maybe those ones are more troublesome than the rest of them. Yeah. So yeah, I mean, we have a bit of error, for example, for I-25 Denver, but then you need to realize that the error is on the scale of the data. And if you remember very well, I-25 Denver has a high amount in terms of the in terms of the air pollution readings measured from that location. So this error is specifically in relation to the amount of the variance itself of what you read in that location. Yeah. So one thing you could do when you're developing models is you don't just want to put all of the whole variables you have decided you want to have in a single model. You could test. You could just say, let me just predict the calibrated version just by the PM 2.5 reading from the low cost. Or maybe I could then add temperature and humidity, or maybe I could add road length, or maybe I could add hour and month. This way, you know how your prediction actually improves when you include some of the signals. And what that does is this. If you do that, right, then you check and then you see. So and then you could pick the best correction model you find. So here is what happened, like I mentioned. So what you do is that you literally just shift. So the corrected one is a blue, the not corrected one is the yellow. So what happens is you just, you essentially just you essentially just change the slope of your of the regression line across this plot here. Yeah. So so if you go down and try to check the errors by location, like I mentioned before, what you then get is that eventually, how do you know that you have made progress with your model? You use your error measurement, which is your mean square error, right? To compare without modeling, what is the error between my my measurement from the sensor and my ground truth measurement? And then when I do modeling, what is this error, right? Because the job of your model is to reduce this error specifically. So if you look at this, for example, you have about 50% reduction in the error in many of the cases, actually, right? So that tells you that, you know what, my model is doing well. And in fact, this is just a linear model 1, which is the case of having just the PM 2.5 reading, right? You don't have all those, road and this and that. You don't have all of that. You just have your 2.5 reading and a linear model, because by changing the slope of that of that regression line, you already correct a lot, right? And that's what happened there. Yeah. So yeah, so what you could do then is, after you understand this whole process and you've gone through this notebook, you want to then get into, trying out new models, adding more features. I have only done the, I didn't add all the roads and, temperature, humidity related features into the model yet. So you could then do that, right? And then what do you want to also check? You want to check your linear regression coefficient. So which of these variables actually make the highest coefficient contribution to this prediction, right? And which ones do not make any significant one that I could also drop, things like that. So that's the exercise that is down here. So I'd encourage you to work on those on your free time. And then you can then go into the lesson 4 notebook, where we now consider things like machine learning, random forest, just to see if you could get some significant improvement. Yeah. So I'll take your questions at this point. Thank you very much for listening so far. Are we there? Do we have the organizers there? Hello?
Yes. Hello. Can you hear me?
Yes.
Hello?
Yeah.
My network is kind of, so it's kind of, it keeps disconnecting me and reconnecting, but I think it's semi-stable now. Awesome. So thank you very much for that wonderful session, Oladimeji. Can you hear me?
Yeah, I can hear you very well, very clearly.
Okay, I think this is really messing up. Hello, can you guys hear me?
Yes.
I think there's a lag. There's a very terrible lag.
Okay.
But,
Danny, I can take him from here. Don't worry if you have any network issues.
So I just need to get the questions and then answer them.
Yeah, I'll take over from here. I'll share the questions with you. Okay. We have some questions now. I'll just read it so to your hearing. Okay, there's a question from Shedrack. He's saying, is it possible to have the training set and the test set as a single set, that is, clean it before splitting instead of working on both individually?
Right, that's a fantastic question, actually. Yes, that's a fantastic question, actually. Yes, it is possible. It is very possible. It turns out to be the case that for this particular data set, right, the training and the test set came in different formats from different, because in fact, the test set sensors were installed later than the training set sensors. So the times do not even overlap. You get, but that is even perfect for us, because this is the actual use case of the correction model. We want to use this correction model in arbitrary locations in that same domain, right? For sensors that we might even install tomorrow, You get, right? So that's why the cleaning happened differently, because we had to correct we had to clean that one differently because it came with a different format, and the file names, or no, what do you call it now? The variable names, right? The column names were different and all that. Yeah. Yeah. So yeah, in many cases that your data comes in a single bulk. So you do the cleaning. Yeah, for sure. Yeah.
Okay, thank you very much for that answer. The next question now says, okay, let me just read it out. He said, I would like to inquire about your usage of remote sensing in the case of study of air pollution. Are you utilizing GIS or continuing to rely on Python? He's saying he's having a hard time understanding the concepts.
Right, that's a very good question. So I tell people to not over focus on the tools. That's why I actually had the first presentation, which is like motivating your problems and understanding what problems you're trying to solve, because you care about solving the problem. You understand? You can then eventually use a GIS or write code or whatever. In fact, nobody cares. What matters is I've come up with a solution, and I understand the problem, and here is my proposed solution, and I have communicated that solution very well. So the key audience that needs to hear what I am trying to say, so that there can be, some policy or action in real life that moves the needle. That said, if you're working with remote sensing data, it turns out to be the case that when you want to do things like, statistical modeling, machine learning, and co, you probably want to work in R or in Python, because that's when you have all the tools to do all of those. But then GIS can help you to like do basic things like initial visualizations and maybe data extractions and all that, right? But eventually, once you want to do like statistical modeling, you want to work in Python or R. Yeah.
Okay, thank you very much for that answer. Before I take the next question, I just want to make an announcement to the interns. The second attendance form will be passed now on Zoom and also on YouTube. All lowercase. When you see it, fill it, and we'll continue now. Okay, moving on to the next question.
Yeah.
It said, please, I need a comprehensive lesson on Python. I've already said, okay, now skip that. Let's go to the next one. Okay, so what about heaviness of vehicle as a factor for the model? It's talking about the heaviness of vehicle as a factor for the model.
Heaviness of vapor, right?
Yeah.
Yeah, that's a very good point. So you want to account for that. And how do you, for example, account for that in your model? Well, so the point is that the heaviness of the vapor, of course, then tells you the amount of PM 2.5 in the atmosphere. But how do you measure the heaviness of the vapor? Right. I would say that you could then use proxy measures. Like, for example, we use roads within vicinity and different kinds of roads, right? So roads of large radius, we are assuming that roads that have very large length, rather, right, or width, right, highways, mean that there are more heavy duty trucks, and there are heavier traffic, meaning that there is more, fumes coming from there. So it's a proxy to this particular point that this person is making now, right? Because you can't specifically measure smoke in the atmosphere, actually, because smoke does not stay in the atmosphere for long enough for even satellite imageries to be able to capture it, because it dissipates very quickly. So what do? You find proxies that could indicate, the presence of smoke, right? For example, if you longitude and latitude is actually a key feature that we didn't include in this. Like, if you say that, the physical location of that sensor plays an important role, like maybe it's in an industrial location, right, where there's a lot of fumes and smoke, and then that could mean, high, amount of smoke in the atmosphere. You just look for proxies to explain this for yourself. Yeah.
Okay, thank you very much for that answer. And moving on to the next question. This one is coming from Oluwakayo. They said, is there a threshold measurement for the root mean squared error? That's for diverse application in linear regression model.
That's a very good point. You're not trying to, so there is no specific threshold. The threshold will depend on you and your understanding of the problem and how how accurate you want to be. So in a case where you're doing a medical application, for example, where, precision is very key, right? So you want to go as close to zero as possible, right? But in the case of air pollution measurement, where you don't think that if a measurement is supposed to be 8.5 and you measure it as 8.7 or 8.9, it makes a significant difference in the in the health outcome for the people. Then based on that, you can formulate and say, you know what, if I get something around an error of one or two, it's not like the end of the world. You're not doing prescription medicine, right? So this is how you come up with these trade-offs. Yeah.
Okay, thank you very much. Thank you very much for that answer. Moving on to the next question. This one is saying, so you have to plot sine of one axis and cosine of the other in order to have a 2D plot. It's asking if you have to plot sine on one axis and cosine on the other.
That's two-dimensional. But in your model, what happens in your model is that you include the sine and the cosine as individual features. You understand? So your model sees that two-dimension, that extra two-dimension.
Mr. Mudele, I think we can hear you clearly. I think you're having an issue. Okay, sorry about that. I think we're having a little technical issue. He will join back shortly. Just give him some few moments. Thank you.
So I actually don't know what happened to my right. So pardon me. Yeah, pardon me. Yeah. I don't know what happened to my PC. It just suddenly disconnected. I am trying to get back to connection, but I am connected with my mobile now. Yeah.
Okay, it's fine. It's fine. It's fine. Thank you. Okay, let's see if we have another question to answer. Okay, saying what proportion of the data set can we set for the training model? That's proportion of the data you can set for training model.
Yeah, that's a good point. Ideally, you want, so people do like this 80-20. It's a general, people default to 80-20, right? But you want to ensure that you have enough data to test your model. But most of your data will go into training, ideally. Yeah. So what people work with about 80-20. 80-20 is a very standard and good start. If you're writing research paper, for example, if you say you did 80-20, it's fine. Yeah.
Okay. Thank you very much. I'm checking if you have any other questions also on YouTube. Okay. But I guess we don't have any other questions for now. Yeah, I see one already. There's just, we can have time for this last question. Saying, he said, what problem is being solved with the code regarding the air pollution project through data science?
Yeah, okay. So what you have done is you've been able to calibrate low-cost sensors using reference sensors and what you the eventual problem you've solved, right? In terms of for example, air pollution monitoring is you then are able to scale your air pollution monitoring in terms of costs, because now you can install low-cost sensors around that give you calibrated measurements, right? So that way you saved a lot of cost, but you still have, very accurate measurements. You get this is the actual key solution if you look at it from a real life application standpoint.
Okay. Thank you very much. Thank you very much for that answer. We're in the aspects of no further questions. I can't see any for now. Yeah, I see there's one just pop up on chat. Okay, he said from Alfred, the same. Could you elaborate on the difficulties that arose during execution of this case study? And the same for instance, were there challenges when obtaining the readings, that is determining the appropriate analysis or constructing the statistical model? I don't know. Let me read it again if you get it.
Okay.
Okay, he said the difficulties you got when taking this case study, that is the challenges when obtaining the readings, that is determining appropriate parameters for the analysis or constructing the statistical model. So what challenges did you get during this case study?
Yeah, you can imagine for somebody who wants to reproduce this, you can imagine that there is a cost. There you have to find, okay, if you're trying to do this kind of thing, then you want to find out where in the location I'm trying to work in, where do we actually have reference sensors? Because if there are no reference sensors, you probably cannot intervene because there's no ground truth, and it's too expensive for you to work because you can't put that in place, right? So that's the first thing. And most of the time, what you want to start with, you want to check airports, because airports actually have air quality sensors. So if you live in a place where there's an airport, or there are embassies, there are large organizations, those people can have those kind of readings. And then you want to ask yourself, are these data publicly available and accessible? Because that's a key question there. Because if you cannot access the data, then there's not much you could do. And then the next thing you do after that, even if you can access the data, is you now want to ask yourself, so low-cost sensors that I want to acquire, right? How many do I need? Setting the whole network up is non-trivial, because that means that you need to actually buy, you need to buy sensors, costs, and then you need the expertise to set it up, and then the data collection process, which is essentially what you do is the collection happens through Wi-Fi. So setting that up also, then once you have that in place, then the data comes to you, and everything else becomes a statistical correction problem, like what we did here. Yeah.
All right. Thank you very much for that answer. That was elaborate enough. I see there's no further question. Thank you very much, Mr. Oladimeji. This was a very, very interesting session. I believe the interns got a lot from this technical session. It was really, really interesting. I enjoyed myself a lot.
Awesome. Yeah, thank you very much too. Thank you everyone interacting with you. Yeah.
Thank you very much. Okay. I guess this is where we'll draw the curtain. This was a very interesting session. Hoping everybody got a good understanding of the concepts. So we've actually come to the end of today's webinar. I thank Mr. Oladimeji Mudele for taking the time to educate us today. Every second has been totally worth it. And I also want to thank you all, our day interns, and also the visitors for joining us today. I'm certain you've gained some valuable insights and knowledge. A big thank you also as well to the Hamoye team and everyone who saw to the success of this webinar. Until next time, do have a lovely weekend. Bye for now.